All right, so let's do part 2 of the alkene reaction mechanisms. So here we're going to do halogenation, halohydrin formation, so X2 plus water, and then oxymercuration, demercuration. All right, so let's start with our halogenation reaction. We'll react that with Br2. And when we're thinking about this reaction, we need to recall that we're not going to form a carbocation, right? That's the key to thinking about all of these reactions. No carbocations are formed, right? And when we do this reaction, we're going to form 3-membered ring intermediates, and we're going to form those intermediates for all of these, right? 2 of these are going to be halogen 3-membered rings, one's going to be a mercury 3-membered ring, right? So what we're going to do is have the alkene attack Br2. Br2 and its electrons will react with the alkene so that we don't form a carbocation, and then we break the bromine-bromine bond, right? So we end up with Br minus, right? And so this is going to be our intermediate, right? And we end up forming bromine going back, right? And again, it's positively charged, right? Plus bromine coming forward. All right, so we form enantiomers, right? So we have enantiomeric intermediates, right? And now Br minus can add, right? And Br minus can add to either side of this, right? There is no regiochemistry that we have to worry about, all right? We'll see when we think about what's happening with these other ones that the reality is that Br minus is going to add to the more hindered side, all right? We'll talk about why that is in a minute. So let's just be consistent and add to the more hindered side in both of these. So if Br minus adds, hopefully it's clear that it's going to add from the side opposite of where the cyclic bromonium bromine is, right? So in the one on the left, the bromine is in the back. It's going to block that face from attack by Br minus, so Br minus is going to add from the front. So in this carbon, we're going to have the Br coming out. That pushes the methyl group back. On the right one, Br is going to stay going back. Right? And then when we look at the other one, we're going to have Br attacking from the back. That pushes the methyl out. Right? And then we have Br on the front, deuterium going back. Right? So when we look at this, definitely the result of anti-addition. Right? So we're going to have this going to be anti-addition. This is going to be a racemic mixture. Right? And again, racemic mixture, those are enantiomers. So we're forming an equal mixture of the 2 enantiomers. Okay? So anti-addition, right, makes sense for getting the bromides. Now, when we do this differently, when we have Br2 and water, now we have to start worrying about the regiochemistry. Right? Where is the OH going to add? Where is the bromine going to add? Right? It's going to start out exactly the same, right? So that we end up with the same intermediates. Now we need to start worrying about where is the OH going to attack. So if this was sterically controlled, we would add the OH to the position where deuterium is. Deuterium is definitely smaller than a methyl group, right? Again, it's just a proton with a neutron, right? So if it was sterically controlled, it would add to that position. We've seen in what we've done in class and what you've read in the book that it actually adds to the more hindered position. So this tells you that this must be electronically controlled, right? And the way to think about this is that in this intermediate, the positive charge is not completely on the bromine, right? Again, we call it a formal charge for a reason. It's just a formality. It's not actually where it is, right? If you think about which of those carbons would best be able to handle positive charge, you're going to put it at the more hindered site, the more substituted site, because that's going to be able to stabilize that charge better. So it turns out there's significant partial positive charge at that tertiary position, right? And since that is more important in this reaction than sterics, that's where the nucleophile is going to add to, right? So when we think about what happens with water, water is going to add to that more hindered position because it is more electrophilic, right? More electron poor. Right, so when we do that, we get two products. So again, we're going to add from the side opposite where the bromine is, right? So in the one on the left, we're going to add from the front, and the one on the right, we're going to add from the back, so that we push the methyl group back here, and we have water adding. Bromine is back. And then the opposite happens for the other one. Right, so again, we form a racemic mixture of these enantiomers. And to finish out the mechanism, all we have to do is do a proton transfer. We have to deprotonate. You can do that with water, or you could do it with Br minus, whatever you'd like to do. So whatever base you want to use. Right, and the key being that you end up with your neutral alcohol products. Right, and again, hopefully it's clear, just like the Br2 addition, that this is an anti-addition, right? So we have OH and Br anti, OH and Br anti, right? So this is an anti-addition, right? And again, we're adding the water to the more hindered position because that's going to be the more electrophilic, right? So our final alkene reaction is oxymercuration, demercuration. Just like hydroboration oxidation, the name really helps you figure out what's going on in each step. Hydroboration oxidation, the first step is hydroboration, so you add an H and a boron. Second step is oxidation, you oxidize the carbon-boron bond. In this reaction, it's oxymercuration, demercuration. So oxymercuration, we're going to add an oxygen and a mercury. Second step, demercuration, we're going to remove the mercury. Right? So the first step is going to look almost exactly like this Br2 and water mechanism, except that we're using mercury in place of Br2. Right? So when we do this reaction, mercury plays the role of bromine, and we do the exact same thing. Right? Alkene attacks mercury, mercury attacks the carbon, and then one of the acetate groups leaves, right? So that we end up with these three murdering intermediates. Right? And just like we talked about with the bromine intermediates, the charge is not stuck completely on mercury. Again, that's a formal charge. That's not really what happens. That molecule is going to spread the charge out as best it can, and there's significant delta plus on the more substituted carbon. So the same thing is going to happen, is that water is going to add to the more substituted side of that cyclic intermediate, right? And again, it's going to look just like what we did for the halogenation with water mechanism, right? So we're going to add water to that electrophilic carbon. And like we said, with the bromine reaction, we're going to get a racemic mixture. Right? We're going to add from the face opposite where the mercury is, because the mercury, like bromine, is very big. It's blocking that face. So we get an anti-reaction. Right? So we're going to add water from the back. Pushes the methyl to the front, right? And that's positive, right? And then mercury is going to stay on the front. And then over here, it's going to be the opposite, where water is coming out, methyl is going back, and mercury is going back. Right? And again, this is an anti-addition. Right? This is a racemic mixture. Okay? We need to do a proton transfer like we did before. Let's try and keep these separate. In this case, we lost an acetate group, so acetate can deprotonate. Right? So if we have acetate, we can grab one of those protons. Right? Same over here. So that's the end of the first step. Now we have to do the demercuration, right? So in demercuration, we use sodium borohydride. We know about sodium borohydride, right? Sodium borohydride is a good nucleophile, right? And sodium borohydride is going to add directly to the carbon where the mercury is, and it's going to be a direct substitution reaction, right? So we're going to have the hydride directly displace mercury. All right, so mercury is going to be the leaving group. Hydride is the nucleophile. And the interesting thing about these direct substitution reactions, this is called an SN2 reaction. These reactions proceed with inversion. So it inverts the stereocenter. All right, so that means when the leaving group leaves coming out, the nucleophile comes from the back. When the leaving group leaves from the back, the nucleophile comes from the front. Right, so that means that we have a really interesting result for the products. So this one, the mercury was in the front, the H comes from the back. So the H is back, pushes deuterium out. Opposite happens here. H is going from the back, so or mercury is going from the back, H comes from the front, and the deuterium ends up going back. All right? So this is just the demercuration step. Right? And again, we said this step in here is a direct substitution. If you want to look up what it is, it's called an SN2 reaction. We'll study that next semester. But the key thing is that the first step here, the oxymercuration part, this one is an anti-addition, just like Br2 in water. The sodium borohydride step is an inversion step, and it turns out that the net result equals a syn addition, which is a little bit strange for us. But if we look at what happened, right, we added OH and H, they're on the same side. OH and H, they're on the same side. So this is one of those strange reactions that the first step is anti, the second step turns that anti-addition into a syn addition because it is inversion. Right? And that's definitely a little bit complicated for us. But with all of this information, again, we now know what's going on with these 7 alkene reactions. Right? And again, I hope that it's clear that these 3 have many, many similarities, right? Just a few differences. And so these aren't, you shouldn't see these as 3 completely different reactions. They give you different products, but they go by very similar mechanisms.